Florian. I am software developer at GTT. I am one of the lead developers of CALPHAD Optimizer, and I'm going to talk about the new version that we released just 2 days ago. I'm really sorry I'm the last presenter for today, but obviously this is going to be the grand finale before the breakout sessions start. So fundamentally, I'm not sure how many of you around here are actually concerned about CALPHAD database assessments, because this is like a subsection of things that we do as like GTT. We do need to generate our self-consistent thermodynamic databases. These need to come from somewhere. Usually we use experimental data. We put it together with a preliminary thermochemical database. We fit those parameters. This is a very intricate process. There's usually a lot of process parameters that go into experiments. They don't have direct expressions in the parameterizations that form the database, but the database has a lot of parameters that we can choose, and all of this is a big negotiation because, as we know, the world is messy, and the databases that we try to come up with try to make sense of a lot of those messy experimental and theoretical data. CALPHAD Optimizer is our approach to this. There is a video playing now which I will talk over, not to talk you through all those details. I'm just trying to briefly show for those of you who have not used it yet what this actually does. So we do have, if you remember this flowchart, we do have the ability to have a good GUI input for experiential data that is somewhat categorized into different types of, we call them recipes, of like what the data actually means in terms of the thermodynamic parameters that can be derived. This is just an example from the CALPHAD Optimizer. So you do get like heat of mixing, you do get liquidus temperatures, solidus temperatures, you do get very recently just added the Gibbs energies for phases you can directly enter as experiments. These are data points that we then use to evaluate against our thermodynamic parameters. These come here, so like this is just one way to display those databases. It's quite similar, not identical to the solution module. It's quite similar, not identical to a lot of those type of systems. It's really just a way to display all of those adjustable thermodynamic parameters. In this case, there's a few of those already selected, and you can change values, you can see the result. What I'm trying to get to is this is a nice GUI that you can use if you want to manually interact with your database, if you want to figure out what's the meaning of certain parameters, what's the effect of certain parameters in your specific database at hand. And then obviously we do have the optimization process. We call this optimization. This is somewhat of a mixture of a badly conditioned minimization problem of the actual error sum, where we compare experimental results to the measured values that we want to have, by adjusting those parameters that we selected beforehand. Depending on the number of parameters you select, it's either very underdefined, very overdefined, or a very clearly defined system. Usually it's somewhere in the mix. This negotiation is something that is usually done with a lot of human input, where the understanding, the domain knowledge, sometimes also the wishful thinking should come in, that we try to parameterize those things. Now, CALPHAD Optimizer does allow you, briefly saw that here, that you can do I made a mistake there when I recorded the video, because I set the value previously manually. Anyway, so this GUI protects you in lots of ways from doing bad things. It also gives you good insight into the current status of an optimization, into the progress, and I'm scrolling down to now the results. So this is like online diagrams that are shown to indicate the progress and the attempted best sets and the iteration of the parameter sets towards that supposedly perfect database at the end. So this is the CALPHAD Optimizer as the GUI program. So why do I show you this? Because I will not go back to this at all. The actual features that I'm going to show you, that I'm going to talk about is, I think I should be done right now, the video. Yeah, I think that's the end of the video. So is that at the end of this optimization, we put great effort into these optimizations being very deterministic. So because the problem space is very vast, is very unclear, there's in previous editions of optimizers of programs that solved these optimization issues, they were very path dependent. So you could be like getting different results depending on how you approach a certain calculation or optimization. CALPHAD Optimizer is very deterministic. We do have quite reliably the best result at the end, given the parameters. And then you also can see, I mean, I circled those in red. You can see that you do get specific values for your parameters that you could directly put into your database. So now, what is not missing from this, but what is really the core point about this is that this is a GUI program, so this is meant to be used by you as humans in a human acceptable way. And now if you look back at this flowchart that I showed, the experimental theoretical data, the thermochemical database, and the fitting process and optimized database in modern times, meaning like not only with the rise of LLMs, but also in the rise of higher throughput calculations, in the ways of having computational derived experimental data and all of these kind of things, we have to ask ourselves a few questions where, like, what is currently stopping us, or not stopping us, but like making it hard for us to work on assessments? What is currently the necessity to kind of like just go through the same motions all over again, right? So like setting up a phase, if you want to do a certain calculation, if you need to create a database for an optimization, you do have to have like a specific dance through the setup of these kind of things. And now, obviously, this is what we had as the main question about this updated CALPHAD Optimizer, is that how can we leverage actually software agents to help us along with this? And to make this a bit visually more easy to understand, I will put up this kind of like, it's not a continuous progress from human to autonomous systems, but rather it's going to be like an estimate of where we think we can save resources, human resources, in exchange for autonomous systems that are employed. So blowing up this flowchart into a much more complex but also more correct flowchart of the workflow, we will now just simply play this kind of simple game of assigning what we think is, what I think as a developer of CALPHAD Optimizer, what can be quite easily done by agents, what can be done by humans, or what has to be done by humans, and where should we put our valuable time, right? Because that's, I mean, software is all about trying to make things more efficient. The easy things is really just that all the setup of assembling a database, assembling optimization, as I said, if we have a fully deterministic way of setting up an optimization and running an optimization, there's not a lot of reason why we would manually interact with that, or why you would hand tune certain parameters if you can just do this in some automated fashion. And then also the just like saving every type of version and all this of files is relatively simple. The other way around, the assessment of experiments, which is like the assessing process, means really just assigning the weights, assigning the relevance of certain data points, all of this. This has to be mostly human. That doesn't mean that you cannot use computational methods, but it has to be very much observably confirmed by humans. In other ways, like these mixed boxes, this is different, right? So we have a lot of those, for example, experiments. If we come from ab initio calculations, we have an a priori understanding of what amount of trust we put into those experiments, so we can also semi-automatically or fully automatically employ those in certain optimization processes, or to specifically execute calculations in specific corners of systems to figure out how we want to progress with the optimization. And then at the very end, at the very bottom, the compare and evaluate. I think there's a lot of ways we can improve by computational methods to figure out good metrics of performance, but the fundamental final sign-off on any type of database, on any type of parameterization, has to be mostly human. So now, after this kind of lengthy introduction, we're going to see what is actually new in CALPHAD Optimizer 3.1. And this is a Gibbs reaction recipe, thanks to Alex, who had a very specific feature wish for this, who put it back on the menu, to be honest. We had it on the list of things we wanted to input anyways, but it's a bit of a longer list, so it never got executed quickly. We do have the sublattice species concentration. That's also that's not directly related, but it's similar to what the previous question was like. So sometimes you want to have deeper insight into a phase internal equilibration, right? So that's the same for the MQM distribution. It's similar to like how you can now target sublattice species concentration in a user-defined recipe. And now the other things that I'm going to talk about are, for me at least as the developer, very much combined into a feature tree that just does not make sense in isolation. So we do have or maybe the TDB database reading support is just a nice gimmick that's not crucial to this path, but still it was a nice gimmick. But we do introduce a CLI interface, and that is mostly to the need of being able to use CALPHAD Optimizer with software agents. And as you just see, could see the video, the GUI program are themselves suitable to use like that as much as when you have something like the CLI interface that I'm going to show. So we're going to start, because I also said like already in CALPHAD Optimizer 3.0, that's the base layer, the foundational pieces to allow what we do right now. That's the ThermML XML database format that CALPHAD Optimizer has switched to, which I guess at some point most of our products will move towards this database format. It's much richer than any of the existing databases. Rich meaning it's a clear superset of all of those database formats. So it does allow to store all the same data and data beyond that. It also is more flexible, and it is better, much better at being written and read by autonomous systems. So this is a clear and very complex topic, how to make data both human and computer readable. It doesn't need to be XML, to be honest. It's XML because it does allow, like, it has a very mature and very powerful validation strategy, and this validation is what I'm kind of just going to give you 2 examples of. One of the things is that you can basically check whether the things make sense, not only based on the structure of the document, but also of the content of the document, and that is something that none of the existing database formats ever allowed. But now you can kind of understand what is internal to such a database to an extent that, for example, you can see from the constituents that you put into a phase whether there is a necessity to have a certain end member present or not. This is not a feature that any of the existing systems has. The solution module somewhat does not allow to not have this, but so like it does go some ways in employing these rules too, but it doesn't do this in such an explicit way, and specifically not in a way that you can say to a computer, try to write an XML file that is valid to that specification, because that's just not going to work because it's a GUI program. ThermML is actually somewhat my personal contribution to the CALPHAD community in general. So it's not, we don't, I mean, I do own this in terms of I host this, but I am open for contributions, and I will very gladly see what some people or what you would contribute or would have as additional to these formats. So this is one of the foundational levels that we need to put in to allow software agents to help us along with these optimizations. The next one is more on the technical side. I will not spend a lot of time here, but previously we had a purely text-based single JSON file to store every information that is in an optimization, which you could interact with. That is absolutely acceptable and fine, but we do want to have more flexibility there, so we move to a zip container that now contains basically the same type of data, but in a more both robust way and also more flexible way, so that we can store and save more files, and still only a single file needs to be moved around by users. So this is really just a minor scaffolding element to the abilities that we're adding. And now the 3.1 edition, the big edition that I just talked about. I think everybody understands what the CLI interface generally means, that we do have a way to interact with the program through the command line, which directly allows agents to use this. I did put some typical use cases here. I don't think we need to go through those. It's fairly clear that this can be done. I have more examples about this. The TDB support is also one thing that I want to mention. It's really just for reading. I don't think anyone's surprised that this is just for reading, because writing TDB format is such a small subset of thermodynamic data, only in such specific shapes that there is really no benefit in writing those files. It's really just, for us, it's really just a legacy support, but it does allow, for example, intake of the tremendous resource that, for example, the S3TE binary databases by Bengt Hallstedt published last year is just it's enormous resource to start interaction, or like to start optimizations with. Okay, now this in the red you can see this is how you can actually do all of these conversions starting from any database into an XML file. So this is something that also agents will use. You don't have to open the GUI. You can just execute those commands. It does work. Like basically all the gray arrow directions work whichever way you want. So this should be fairly straightforward to use. The next one is also, I think, mostly requested by Cassie, because Cassie does high throughput evaluations in building GTOX, which requires her to run multiple evaluations after adapting certain parameters, and then she wants to look at results of her experiments, and it's very nice to have visual results, right? So it's always easier to have a visual result of, I don't know, 10, 15, whatever type of points. And you can run optimizations, and then you can receive a summary. The summary kind of just looks like this, but it does give you a very easy and fast, like this one's just a single iteration, so it didn't really optimize, so the values aren't updated, but it does give you an overview of what are the parameters, how did they update, and what is the total error sum. This is very helpful just to see whether it converged or where it converged. And the other part that you can get is per recipe that is in, or per experiment that is in the OptX container, you do get a kind of like cookie cutter type of plot of the results. These plots are not the same as in the GUI. The optimization result will be the same as the GUI, but the plots are not, because these plots are, they have to be a bit differently generated. Obviously, there's different libraries involved in all this, but to just understand your results, these should be totally fine. Okay, then there's a bit more of the controlling side of things. I can go very fast. So if you want an agent to know the status of your optimization, you do need to be able to introspect this one. And now there is like this options of showing progress every, and then there's like a number of iterations. So you can say how many times you want to get results. You will simply get all of those parameter values. You will get the error sum contributions, and you get the amount of iterations it took to get there. This is really just simple and straightforward to be able to inspect what's going on, because I'm not sure who is running longer runs of those, but CALPHAD Optimizer may run into minutes or tens of minutes if you have really complex systems. There's more of those. There is you can create those files, you can assemble those and disassemble those. There's really just the containerization. This is needed for the agents to interact with the components of that zip file confidently, and it's also very helpful if you want to say, I want to migrate my parameter set basically from a binary to a ternary system or something like that. You need to unpack and reassemble these type of data sets. This is really just examples. There is the unpacking is the opposite of the creating, and then the renaming was something that I added because it's very helpful if you want to say run different sets of optimization parameters against against the same data set, for example, and then you need to have like different output and all of this, and it's much easier if you don't have to do this manually, but let the agent do this. Also, another kind of like legacy support is just you can use an old opt file and convert it into a new one, so the amount of input you need to give to continue using your old files should be minimal this way. Okay, this is now all kind of just the place where we want to be, and now I can show that this does work. So now this is kind of like the LLM interface. We thought about this, and I guess also you could hear that previously we said there is context files and then in brackets skills. So I did present at CALPHAD like 3 weeks ago about actually using skills MD files, or like the more formalized ways. I kind of took a bit of a step back, because the only thing that you actually need is somewhat of reference material to explain to an LLM what you're doing. It's not so much like the shape, the orchestration, all of this. This can come from just the general knowledge of the agent. It doesn't really need to be highly specific to thermodynamic calculations. What we do need is to have reference material. We do provide that reference material, so there is like basically just a file that just explains all those command line options, and this is, I would say, like this is 99% enough to do this. So this is what the LLM interface provides, and just to somewhat, I wouldn't say it's proving anything, but I can show you what can be done. So like this is, I think it's always a bit lengthy to read these out. I don't want to read them out, but I will tell the agent without opening CALPHAD Optimizer, with just like telling him there is this documentation piece. There is this CLI.exe in the installation directory, and now please go on and continue those, continue to find and assemble the ternary system from the binary systems, and then give me an opt-x file for the optimization, and then also include some stub experiments. Stub experiments just means because there's also schema validation for the experiments that's already been in CALPHAD Optimizer for a while, so this isn't a new feature. The agent can actually testify that the experiments that it is creating are valid with respect to the schema, and therefore they can be opened in CALPHAD Optimizer. And just by this one prompt, I do get a database that does not fail on loading the experimental data or loading the optimization, and then it loads the optimization settings, and there it says undefined because it actually did not put any of the optimizers in there, but that's very easy to correct. And you can see there's a stub liquidus temperature for the FCC, for the BCC, and whatever else. I didn't check particularly whether these make sense, because also if you can see the prompt, I didn't actually say there to put meaningful data. But this gives you quite a lot of the initial start to this. I do have one more example. I have to do a few more examples. This is the prompt that Moritz supplied to me, and I had to modify because it was just very ambitious, and there was a proposal in there and all of this. I don't want to show this. So really you can even go like further up in the logical chain, right? So like it's not so much about I have this one chemch file and there's a TDB, and then I want to do this and I need to look up which is the correct phase model for that or anything like that. Certainly you should be able to check this and to validate all of this, but it's not necessarily needed. So you can also ask, I'm kind of trusting you that you will put something together. And because of the validation rules and the ThermML schema validation and all of those kind of like robust steps we can do now with the CLI, what comes out of this one prompt is actually I would say a considerably okay attempt at modeling a rhombohedral move phase for this system. Obviously the data that's in there doesn't make much sense, but the structure makes sense, the prototype makes sense. It's like I didn't check much further down the file, but like it's a good first draft, and I wouldn't expect more given this prompt, to be honest. There's also a experimental set of data where you can see just from the title, this is hinting at this is data that would inform an optimization that you can run in this data file, and it's also consistent with what you had in the, or what is in the opt-x container in terms of the database, so the phase names that are referred to, even though this one's a very weird one, even though like this is, it's a bit weird, but this is also like what agents do. You do get quite a bit down, kind of like all the notches of, oh man, I do need to find data for this and for that and this, so you can just kind of get started with. The last example that I have, or I think the second to last example, is maybe a bit more natural one. So I just used the PBSN example, and I said I want to add the HCPA3 phase to this optimization. This doesn't need to make sense, but it is like this, and I want to add iron, and then can you also add accommodate this in all the other experiments, which means just like adding a column that is iron 0, for example, like, and this is something that is just tedious to do manually. It can be done very easily by just a simple prompt. This also takes just seconds to do, and then also I say create a solubility experiment that is filled with 10 data points, which I'll supply later. So then you do get this as a two-phase equilibrium with certain compositions. Obviously these are made up, but everything else is somewhat fine and somewhat easily adjustable to your actual needs. I think now this is actually the last example that I've had, and that is something where I just say, well, we can also add compounds, and the compounds, I can create those rules, and what it actually does, these are simple things, but it takes effort to do this, and you can see it does absolutely nail the Gibbs expression. It does absolutely do the nonsense that I asked it to do, because I asked like these don't exist, these compounds, but it's still, this is fair data. It did add it correctly, and it did also add the experiment, and then I did the dry run, like I didn't, but the agent ran this plot without an optimization kind of thing, and then you can see obviously the data points do not make sense, but they do make sense that this is actually the liquidus temperatures of the PBSN binary without those compounds. And I think I may have, I don't know about time, like I wanted to be good on time, so I am good on time this time around. So everything can be continued. I said right now I would really like to have a drink first, but in the breakout session on CALPHAD Optimizer 3.1. Thank you for your attention.